Now that we have been exposed to logarithms, we are going to use them to evaluate non-integer exponents. In this lesson, I will rely heavily on results from previous lessons, so if you're not very familiar with this topic and haven't seen those videos, you might be a bit lost. We start with this change of base expression for an exponential. Any base b1 raised to x times a constant c can be made equal to another base b to the x. One of the more useful changes of base is to make b1 equal e, which is approximately 2.718, as we have seen elsewhere. In our example, we want to express 2 to the x as e to the c times x. So 2 equals e to the c. How do we know c? By trial and error, we already tried c equals 0.693. That has 3 digits and gives us 3 digits past the decimal in our answer, 1.999 versus 2 exactly. What if we guess c accurate to more than 3 digits? How about c equals 0.69314718? That is accurate to 8 digits, and plugging it into the proper Taylor series gives us 8 digits in the answer, as underlined in red. So how did I get those 8 digits? They come from the natural logarithm of 2, which we calculated with a series expansion in the previous lesson. Here I have rounded it to 8 digits. Now I'm going to use the laws of logarithms to justify a few of the things I just said. Not surprisingly, these were already covered in a separate lesson. The same laws apply to any base, including base e, so here I've simply rewritten the exact same rules, but replaced the generic log with natural log, ln. Specifically, we will use the rule boxed in red in the first step, then we will use the rule in purple to rewrite things a bit. That algebra can be seen here. The argument b to the x can be rewritten according to the right-hand side in the first line, because e to the natural log cancels. Then the x comes out front. We swap the order and it becomes evident that the constant c is equal to the natural log of b. That's why we use the natural log of 2 for 2 to the x. For convenient reference, here is the series expansion for the natural log. We use the geometric series to derive it. Back to this page now. I'm going to plug the number in green into our series expansion for the exponential function, e to the x. Remember that is just the natural log of 2 rounded to 8 digits. And we used the series expansion on the previous screen to find that number. Those calculations are seen here. The series itself converges to 10 digits past the decimal, as seen underlined in purple and red at the bottom of the 4th and 5th columns, respectively. That is not to be confused with the 8 digits of accuracy in our answer. There are 8 9s and then 2 8s. We would need 10 9s to have 10 digits of accuracy. Alright, so back to this example. We want to find 2 to the 3.761. That is a non-integer exponent. We have already discussed various approaches to obtaining this number to many digits of accuracy. Now we will see how the logarithm makes the task more manageable. The first step is to multiply our exponent 3.761 by c, which is the natural log of 2 in this case. So we are evaluating e to the number seen in the last line. As we've seen many times in this lesson series, e to the 2.606 can be split into the product of e squared and e to the 0.606. E squared is underlined in orange. That is simple multiplication because 2 is a whole number. 0.606 needs to be plugged into the Taylor series. Smaller numbers converge faster, so we will divide it by 4 and then raise our answer to the 4th power at the end. The final answer for this sub-step is underlined in blue here. Here is a spreadsheet showing the calculation of that Taylor series. Notice convergence to 14 digits past the decimal, as seen in the last row of the fourth and fifth columns. The number underlined in the last column is the same one we just saw on the previous page. This is the one raised to the fourth power. Now we can multiply the two exponentials together. That result is approximately 13.55, as seen in the last line. If I were to plug in 2 to the 3.761 into a scientific calculator, I would get the number in the last line. Compare that to our answer immediately above it. That is accurate to 8 digits. Interesting how we started with the natural log of 2 rounded to 8 digits. Coincidence? Compare that to the first time we tried this trick. We started with 3 digits in c equals 0.693. Our final answer of 13.5 was accurate to 3 digits. Are you noticing a pattern? By the way, here's how to evaluate the number 2 to the 3.761 directly on a scientific calculator. You must press 2, then the button boxed in red, followed by 3.761, equals. Whereas I'm not entirely certain how exactly the algorithm works, I would guess that it uses some trick involving logarithms and exponents, like the example I just walked us through. We started with 8 digits and our answer was accurate to 8 digits. What if I wanted more digits of accuracy? I'd have to include more digits in the input, the natural log of 2. Let's have a discussion in the comment section below. I appreciate the opportunity to explore these topics with you and look forward to more discoveries in the future. Thanks for watching.